Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring astrophysics, the cutting-edge science that asks how the universe works at its deepest and largest scales. This is the realm where stars are born from collapsing clouds, where black holes bend time, and where invisible matter shapes entire galaxies without ever shining. It is a field built on light, gravity, and patience. From a single flicker in a telescope, scientists can uncover the age of a star, the motion of a galaxy, or the chemical history of worlds we may never touch. Astrophysics shows us that the night sky is not still. It is active, strange, and full of hidden forces. Space itself is expanding. Ancient light still carries the memory of the early universe. And somewhere far away, stars are dying in explosions powerful enough to forge the elements inside your own body. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is get settled in. Let your shoulders soften. Let your breathing slow, and allow the day to gently fade away as we explore the vast science of the cosmos together. Let's begin. The universe still glows with leftover light from its fiery beginning. Long before stars existed, the cosmos was hot, dense, and filled with charged particles that scattered light in every direction. It was not transparent. It was more like a luminous fog. As space expanded, everything cooled, and electrons finally joined with atomic nuclei to form neutral atoms. At that moment, light could travel freely for the first time. That ancient radiation has been moving through space ever since. Expansion has stretched it into microwaves, far colder and weaker than visible light, but still detectable across the sky. This glow is called the cosmic microwave background. It is not coming from one distant place. It surrounds us from every direction because it comes from the early universe itself. Tiny variations in its temperature show where matter was slightly denser, and those slight differences later grew into galaxies. In a very real sense, the night sky carries a baby picture of the cosmos. Space itself is stretching, carrying distant galaxies beyond future reach. Galaxies are not simply flying outward through a fixed emptiness. The distance between faraway galaxies grows because space itself expands. This idea changed humanity's picture of the universe. Instead of a static cosmic stage, astrophysics revealed a changing fabric. Light from distant galaxies is stretched as it travels, shifting toward redder wavelengths. The farther away a galaxy is, the more strongly this stretching appears. Over immense time, some galaxies will recede so far that their light can never reach future observers. They will pass beyond a cosmic horizon, not because they crossed an edge, but because expanding space prevents their signals from ever arriving. Future civilizations in a very old galaxy may look up and see a much emptier universe than we do. The evidence for cosmic expansion comes from careful measurements of light, not guesswork. It tells us the universe is not only large, it is becoming larger with every passing moment. Gravity does not pull instantly because its influence travels at light speed. It is tempting to imagine gravity as an immediate force connecting everything at once. Modern physics says otherwise. Changes in gravity travel through space-time at the same speed as light. If the sun could somehow vanish, Earth would not respond instantly. For about 8 minutes, our planet would continue along as though nothing had happened, because that is how long light and gravitational information take to cross the distance. This does not mean gravity is weak or uncertain. It means the universe has a speed limit for cause and effect. The same principle allows gravitational waves to move outward from merging black holes and neutron stars. When massive objects accelerate, their changing gravitational fields spread through space, not instantaneously, but as ripples moving at cosmic speed. This makes gravity feel less like an invisible rope and more like a dynamic property of space-time. Even the pole that keeps worlds in orbit obeys the pace of light. Black holes can slow time until the universe outside races ahead. Near one of these objects, gravity is not merely strong. It changes the pace at which moments pass. This comes from Einstein's theory of relativity, where time and space are woven together and warped by mass. Far from a black hole, a clock may tick normally. Closer in, that same clock would appear to run more slowly to someone watching from a safer distance. The effect grows stronger near the event horizon, where escape becomes impossible. To the falling traveler, time might feel ordinary for a while. To the outside universe, their descent would seem to stretch and fade. This is not an illusion caused by faulty clocks. It is the universe keeping time differently in different places. The idea sounds almost like fantasy, yet it is built into the mathematics that also helps GPS satellites work. Around a black hole, time is not a background. It becomes part of the drama. Every atom in your body was shaped by ancient stars. The calcium in your bones, the iron in your blood, and the oxygen you breathe were not born on Earth. They were made through cosmic processes that began long before the solar system existed. In the hearts of stars, lighter elements are fused into heavier ones under immense heat and pressure. When massive stars reach the end of their lives, they can explode and scatter those ingredients into space. Later, those enriched clouds collapse again, forming new stars, planets, moons, and eventually living things. This means your body is not separate from the universe. It is made from material that has already passed through stellar furnaces, ancient explosions, and drifting interstellar clouds. The atoms inside you have been travelers for billions of years. They crossed the galaxy before they became skin, breath, thought, and heartbeat. Astrophysics turns this into something measurable. We are not only looking at the stars. In a literal sense, we are made from them. Most cosmic matter is invisible, yet it steers entire galaxies. When astronomers measure how galaxies spin, they find something strange. The visible stars and gas do not provide enough gravity to hold them together at the speeds observed. Outer stars should drift away, yet they remain bound in great rotating systems. The best explanation is that galaxies are surrounded by vast halos of unseen matter. It does not shine, absorb, or reflect light in any ordinary way. We notice it only because gravity reveals its presence. This hidden mass shapes how galaxies form, how they cluster, and how light bends across deep space. Without it, the universe we see would look very different. Stars might not have gathered into such grand structures at all. Dark matter is one of the most successful ideas in modern astrophysics, yet its identity remains unknown. It may be made of particles we have not discovered. For now, it is an invisible architecture, holding the bright universe in place. Neutron stars crush a sun's mass into a city-sized sphere. After a massive star explodes, its core can collapse into one of the strangest objects known. Gravity squeezes the remaining matter so fiercely that atoms are shattered. Electrons and protons combine into neutrons, producing material so dense that ordinary comparison almost fails. The object left behind may be only about the width of a major city, yet it can contain more mass than our sun. A sugar cube-sized piece would weigh as much as a mountain, if such a sample could somehow exist on Earth. These remnants are not just heavy. They can spin rapidly, hold extreme magnetic fields, and distort space-time around them. Their surfaces may have gravity billions of times stronger than Earth's. They are the universe showing matter under conditions no laboratory can truly recreate. A neutron star is what happens when a stellar core refuses to become a black hole, but is compressed almost to the very limit. Ripples in space-time have reached Earth from colliding black holes. For decades, gravitational waves were a prediction, waiting for proof. Einstein's equations suggested that violent cosmic events should send faint distortions through the fabric of space-time, moving outward at light speed. The challenge was that by the time these waves reached Earth, they would be incredibly small. Then detectors finally measured a signal from two black holes spiraling together and merging far away. The passing wave changed the lengths of long laser tunnels by less than the width of a proton. Yet that tiny shift carried information from one of the most powerful events in the universe. It was not light, sound, or particles in the usual sense. It was space-time itself, trembling. This opened a new kind of astronomy. Scientists could now study objects that might emit little or no light at all. The universe had given us another sense, and with it, a new way to listen to darkness. The James Webb Space Telescope can study newborn galaxies that formed near cosmic dawn. This telescope was designed to look into the infrared, which is essential for studying the earliest galaxies. As the universe expands, light from very distant objects is stretched on its journey toward us. What began as ultraviolet or visible light can arrive as infrared radiation after traveling for billions of years. Webb's golden mirrors collect that faint, ancient glow with extraordinary sensitivity. This allows astronomers to examine galaxies from a time when the universe was young and still building its first large structures. Some appear surprisingly bright or mature for their era, which has sparked new questions about how quickly stars and galaxies formed. Webb also looks through dust that blocks visible light, revealing hidden regions of star birth. It is not just taking beautiful pictures. It is measuring chemistry, motion, and history in objects near the edge of observable time. With Webb, cosmic dawn is no longer only an idea. It is a place we can investigate. Quasars can outshine galaxies while feeding on falling matter. At the centers of some distant galaxies, supermassive black holes are surrounded by disks of gas spiraling inward. As that material falls, it heats to extreme temperatures and releases enormous energy before crossing the point of no return. The result can be a quasar, one of the brightest steady sources in the cosmos. A single quasar can shine more intensely than all the stars in its host galaxy combined. Some launch jets that stretch across distances larger than galaxies themselves, driven by magnetic fields and high-energy particles. Because many quasars are far away, their light often began traveling when the universe was much younger. They act like brilliant beacons from deep time. By studying them, astronomers learn about early black hole growth, galaxy formation, and the gas between galaxies. A quasar is powered by darkness, yet it becomes one of the most luminous signs that matter can leave behind. Astrophysics reveals that reality is stranger than imagination, but measurable. The strength of this science is not only that it describes astonishing things, it tests them against the universe. Ideas about invisible matter, expanding space, stellar death, and black holes all sound extraordinary at first. Yet they survive because observations keep pointing toward them. Telescopes collect light from distant objects. Detectors register particles and gravitational waves. Spectra reveal chemistry from across space. Mathematical models make predictions that can fail, and that is what gives the field its power. Astrophysics asks enormous questions, but it answers them with measurements. How do stars shine? Why do galaxies hold together? What happened when the first atoms formed? Each discovery begins as a signal, faint enough to be missed, then becomes part of a wider story. The result is a universe more surprising than myth, but not beyond understanding. It is a place where wonder does not replace evidence. Wonder grows stronger because the evidence is real. Light from distant stars arrives as a message from the past. When you look at a star, you are not seeing it as it is right now. You are seeing light that left its surface earlier, sometimes years ago, sometimes thousands of years ago, and in distant galaxies, billions of years ago. Light moves incredibly fast, but space is so vast that even light takes time to cross it. This turns astronomy into a kind of time travel. The night sky is layered with different ages. A nearby star may show a recent past, while a faraway galaxy may reveal conditions from when Earth had not yet formed. Telescopes do not merely magnify objects. They gather old light and let us read what the universe was doing when that light began its journey. Some of those photons travel through dust, gravity, and expanding space before reaching a mirror or detector. By the time they arrive, they have become messengers from places and times beyond human reach. A star is balanced between crushing gravity and outward nuclear fire. A star survives because two immense forces reach a delicate agreement. Gravity pulls everything inward, trying to compress the star under its own weight. Deep in the core, pressure and temperature rise so high that atomic nuclei fuse together, releasing energy. That energy pushes outward, creating pressure that resists collapse. For most of a star's life, this balance remains stable. The star does not explode, and it does not fall inward, because the two forces hold each other in check. Our Sun is in this long middle phase now, steadily fusing hydrogen into helium. If fusion slows, gravity gains ground. If fusion surges, the star expands until conditions settle again. This balance is not fragile in the ordinary sense. It can last for billions of years. Yet it also cannot last forever. When fuel runs low, the agreement breaks, and the star begins the next chapter of its life. The Sun loses mass every second by turning matter into light. At the heart of our star, hydrogen nuclei fuse into helium. The final helium nucleus weighs slightly less than the original ingredients. That missing mass has not disappeared. It has become energy, following Einstein's famous relationship between mass and energy. The Sun releases that energy as radiation, including the light that warms Earth and powers much of life. Every second, millions of tons of mass are converted into energy inside the solar core. That sounds enormous, yet the Sun is so massive that it can continue this process for billions more years. The light begins in the core as high-energy radiation, then works its way outward through countless interactions before escaping into space. When sunlight touches your skin, it carries the result of nuclear fusion from a star 93 million miles away. The Sun is not burning like wood or coal. It is slowly turning a tiny part of itself into morning. Massive stars live fast because they burn their fuel fiercely. A star with far more mass than the Sun has a stronger gravitational squeeze at its core. That pressure drives fusion at a much higher rate, creating a brilliant output of energy. It may seem that a bigger star should live longer because it has more fuel, but the opposite is true. It spends that fuel extravagantly. Some massive stars shine tens of thousands of times brighter than the Sun, and their lifetimes may last only a few million years. In cosmic terms, that is brief. During that short existence, They can create heavier elements in layered shells, like an onion made of nuclear reactions. Their fierce radiation sculpts nearby gas clouds and can trigger new waves of star formation. When their cores can no longer support them, many end in spectacular collapse and explosion. Massive stars are rare, but they have an outsized role. They live quickly, change their neighborhoods, and die with consequences that echo through galaxies. Red dwarfs may shine quietly for trillions of years. These small stars are the most common kind in the galaxy, yet none has lived long enough to reach old age. The universe itself is not old enough. Red dwarfs burn hydrogen very slowly and efficiently, using their fuel with remarkable patience. Their interiors can keep material mixed, which helps them access more hydrogen than larger stars can. Because they are cool and dim, they may shine for trillions of years. Long after brighter stars have died, red dwarfs could remain as steady points of light in an aging cosmos. Many are too faint to see with the naked eye, but they may host planets in close orbits. Around such stars, the habitable zone lies near the star itself, which raises questions about radiation, tides, and planetary atmospheres. Red dwarfs remind us that the universe has long futures as well as ancient pasts. Some stars are not brief fireworks. They are slow burning lanterns of cosmic time. Blue stars are rare because their lives end quickly. A blue star announces extreme heat at its surface. Its color comes from radiation shifted toward shorter wavelengths, which reveals a star far hotter than the sun. These objects are often massive, intensely luminous, and visible across great distances. They can dominate young star clusters with their brilliance, but they do not remain for long. Their cores consume fuel at a ferocious rate, and their radiation can blow strong stellar winds into surrounding space. Some shed material so dramatically that they carve bubbles in nearby gas. Because their lifetimes are short, blue stars usually point to regions where star formation happened recently. They are cosmic signposts of youth. A cluster full of them tells astronomers that it has not had much time to age. Though rare, they shape their environments powerfully. They flood nearby clouds with ultraviolet light, influence newborn stars, and often prepare the stage for violent endings. A dying star can seed space with carbon, oxygen, and iron. Stars are not only lights in the dark. They are makers of elements. Over a lifetime, fusion builds new atomic nuclei in a star's interior. In lower-mass stars, carbon and oxygen can be exposed and released as outer layers drift away. In more massive stars, advanced fusion stages can create elements up to iron in the core. Iron is a turning point because fusing it no longer produces useful energy for the star. Once the core can no longer support itself, collapse may follow. The resulting explosion can throw enriched material into space at tremendous speed. That expanding debris mixes with interstellar gas, becoming part of future star systems. A rocky planet, a shell, a tree, and the human body all require ingredients from earlier generations of stars. Stellar death is not merely an ending. It is one way the universe recycles matter into new forms of complexity. Supernova can briefly shine brighter than their entire home galaxy. When certain stars explode, the release of energy is so immense that a single event can rival the combined light of billions of stars. For days or weeks, the supernova may become the brightest object in its galaxy. Astronomers can detect some across vast cosmic distances, which makes them powerful tools for studying the universe. These explosions happen through different pathways. Some mark the collapse of massive stellar cores. Others occur when a white dwarf in a close system gains too much mass and detonates. In both cases, the event transforms the surrounding space. Shock waves race outward, heating gas and spreading newly made elements. The expanding remnant can glow for thousands of years, becoming a laboratory for high-energy physics. Supernovae are terrifying in scale, but they are also creative. They enrich galaxies, stir interstellar clouds, and help set the conditions for later stars and planets. A death can become a beginning. White dwarfs are stellar embers packed with astonishing density. When a sun-like star exhausts the fuel in its core, it does not usually become a black hole or a neutron star. Instead, it sheds its outer layers and leaves behind a compact remnant. This object is roughly Earth-sized, yet it can contain a large fraction of the Sun's mass. Its atoms are squeezed into a state where ordinary thermal pressure is no longer what holds it up. Quantum physics provides the resistance through electron degeneracy pressure, a rule of nature that prevents electrons from being packed into identical states. A white dwarf no longer produces energy through fusion in the usual way. It shines because it is still hot from its earlier life, cooling slowly across immense stretches of time. Some sit alone in space. Others orbit companion stars and can draw material from them. These remnants are not ashes in a fireplace. They are dense, glowing fossils of stellar evolution. Some dead stars cool slowly into theoretical black dwarfs. A white dwarf does not vanish when its glow fades. It simply keeps losing heat into space, little by little, across stretches of time so vast that the present universe is too young to contain the final result. The predicted end state is a cold, dark stellar remnant that no longer gives off meaningful light. This object has never been observed because even the oldest white dwarfs have not had enough time to cool that far. The idea is fascinating because it points beyond the familiar age of the cosmos. We can describe an object that should exist only in a future so remote that galaxies themselves may look different. A black dwarf would be like a memory of a star, still holding mass, still obeying gravity, but no longer shining. It would be a fossil of light, a quiet endpoint for stars like the sun after their long lives have faded into darkness. Pulsars sweep beams through space like cosmic lighthouses. A pulsar is born when a collapsed stellar core becomes both extremely dense and rapidly spinning. Its magnetic field channels radiation into narrow beams that stream from its magnetic poles. If one of those beams crosses Earth, radio telescopes detect pulses arriving with remarkable regularity. Some pulse many times each second, keeping time so steadily that they rival the best human-made clocks. This precision has allowed astronomers to test gravity, study interstellar gas, and even search for tiny disturbances caused by gravitational waves. The pulsing itself does not mean the star is flashing on and off. It means the beam is sweeping across our line of sight as the object rotates. In space, orientation can decide whether something appears silent or spectacular. A pulsar may be sending radiation in powerful beams for ages, but only worlds in the right direction ever notice its rhythm. Magnetars have magnetic fields strong enough to distort atoms. Among neutron stars, magnetars are the extreme members of an already extreme family. Their magnetic fields can be 1,000 trillion times stronger than Earth's. Near the surface, ordinary atoms would be stretched and warped by magnetic forces beyond anything familiar. These objects can unleash sudden eruptions called starquakes, where the rigid crust shifts under magnetic stress. The result can be a blast of X-rays and gamma rays visible across huge distances. A magnetar flare detected in our galaxy once affected Earth's upper atmosphere, even though it came from many thousands of light years away. These stars show that magnetism is not just a classroom force moving compass needles. In the right cosmic setting, it can shape matter, store enormous energy, and release it with stunning violence. A magnetar is a reminder that the universe takes familiar forces and magnifies them until they become almost unrecognizable. A neutron-star merger can forge gold and platinum. When two neutron stars spiral together, their final collision is not only a gravitational spectacle, it is a cosmic foundry. These stars contain matter packed so tightly that the merger throws out neutron-rich debris at incredible speeds. In that expanding material, atomic nuclei can rapidly capture neutrons, building heavy elements that ordinary stellar fusion cannot easily produce. This process can create gold, platinum, uranium, and other rare ingredients. When astronomers observed such a merger, they saw a fading glow called a kilonova, whose color and behavior matched the production of heavy elements. It was a powerful confirmation that some of Earth's most treasured metals may have come from collisions between dead stars. Every gold ring, every platinum instrument, every trace of certain heavy atoms carries a history older and stranger than mining. Their story may begin in a flash, where two stellar remnants became one and scattered treasure through space. Gravitational waves let scientists hear events that telescopes cannot see. Light is not the only messenger in the universe. Some of the most dramatic events happen in darkness, hidden by distance, dust, or by the nature of the objects involved. Gravitational wave observatories give scientists another way to detect them. They do not record sound in the air because space has no air to carry it. Instead, they measure tiny changes caused when space-time itself is squeezed and stretched. The signals are often converted into audio, so researchers can hear rising chirps from compact objects spiraling together. Each pattern reveals masses, spins, and the violence of the final moments. This is like listening to a locked room through the walls of reality. Telescopes show the universe through light. Gravitational wave detectors reveal motion in the fabric underneath. Together, they turn astrophysics into a richer story, where some events are seen, some are heard, and some are understood only when both messages arrive. Black holes are not empty holes, but regions of trapped space-time. The name can be misleading. A black hole is not a tunnel punched into a cosmic floor. It is a place where mass has curved space-time so severely that every future path inward leads deeper in. The darkness comes from the fact that light cannot escape once it passes the boundary. Outside that region, gravity behaves in a way that still follows rules. A planet could orbit a black hole if it stayed far enough away. The strange part is not that a black hole is a vacuum cleaner swallowing everything nearby. The strange part is that geometry itself becomes a trap. Paths that would normally lead outward bend toward the center. Scientists describe this with equations, but the idea remains startling. Space and time are not passive surroundings. Under extreme gravity, they become the architecture of captivity. A black hole is not emptiness. It is the shape of no return. A black hole's boundary is called its event horizon. This surface is not made of fire, metal, or any solid material. It is a point of commitment. Outside it, a rocket with enough power could, in principle, escape. Inside it, no signal can ever travel back to the wider universe. The boundary gets its name because events within it cannot influence observers outside, at least not by sending light or ordinary information outward. For a very massive black hole, crossing the horizon might not feel dramatic at the exact moment. There may be no physical wall, yet the meaning of that crossing is absolute. Afterward, every possible route through space-time points inward. The event horizon separates the knowable from the unknowable. It gives astrophysics a rare kind of natural border, not an edge of matter, but an edge of communication. We can study what happens around it with telescopes and simulations. What happens beyond remains hidden behind the universe's strictest curtain. Nothing escapes an event horizon once it crosses inward. The reason is deeper than ordinary speed. You might imagine that a faster engine could simply climb out, but inside this boundary, outward no longer works the way it does elsewhere. The geometry of space-time is tilted so completely that all future directions lead inward. Light, which travels at the greatest possible speed, cannot find a path back out. Since nothing can outrun light, everything else is trapped too. This is why the event horizon is so important. It does not merely mark where gravity is strong. It marks where escape has become physically impossible. The material that falls through may have once been gas, dust, a star, or radiation. But after crossing, it cannot report its journey. To outside observers, only indirect clues remain. Mass, spin, and electric charge can still shape the black hole's exterior. The details of what fell in are hidden from view, leaving a profound mystery behind a mathematically clear boundary. Black holes can spin fast enough to drag space-time around them. Rotation changes the story. A spinning black hole does not sit in space-time like a still weight on a sheet. It twists the surrounding fabric as it turns. This effect is called frame dragging, and it means nearby space is carried along in the direction of rotation. Close enough, an object cannot remain perfectly still relative to the distant universe. It is forced to share the motion in some way. Around a rotating black hole, there is a region outside the event horizon called the ergosphere, where this dragging becomes unavoidable. In theory, energy can even be extracted from that region, as if the black hole's spin were a cosmic battery. This may help power some of the jets seen from active galactic centers. Spin turns black holes from simple traps into dynamic engines. They do not only curve space-time. They can twist it, stir it, and shape the behavior of matter nearby. Stephen Hawking showed black holes may slowly leak radiation. Classically, these objects seemed perfectly dark. Quantum physics complicated that picture. In the 1970s, Hawking combined ideas from gravity, thermodynamics, and quantum theory to show that black holes should emit a faint form of radiation. This does not come from matter simply flying out from within the event horizon. It arises from quantum effects near the boundary, where the presence of the horizon changes what empty space can do. The smaller the black hole, the warmer and more active this radiation should be. Large astrophysical black holes radiate so weakly that the effect is far beyond present detection. Even so, the idea is profound. It suggests that black holes have temperature, entropy, and a slow path toward evaporation. That creates deep puzzles about information and the foundations of physics. A black hole may not be an eternal prison after all. It may be a very slow process, patiently returning energy to the universe. The first black hole image revealed a glowing ring of hot gas. When scientists released the image from the Event Horizon Telescope, the picture looked simple at first, a dark center surrounded by a lopsided orange ring. Yet behind that image was a planet-wide network of radio observatories working together as one enormous virtual telescope. The target was the central black hole in the galaxy Messier 87. The ring showed radiation from superheated material moving near the event horizon, shaped by gravity so intense that light curved around the object. The dark region was not the black hole itself in a photographic sense. It was its shadow, created by captured light and bent paths around the horizon. This was a triumph because black holes had long been studied through indirect evidence. At last, their immediate surroundings had been resolved in detail. The image gave the world a visual proof of gravity's strangest prediction, not as an artist's idea, but as data turned into sight. Sagittarius A sits quietly at the Milky Way's hidden center. At the heart of our galaxy lies a compact object with millions of times the Sun's mass. It is difficult to see directly because thick dust and gas block visible light along the galactic plane. Astronomers uncovered it by watching stars whip around an unseen center at extraordinary speeds. Their orbits reveal a massive object packed into a region far too small to be anything ordinary. Compared with some galactic centers, ours is relatively calm. It is not currently blazing as a powerful quasar. Instead, it flickers and flares as small amounts of material fall toward it. This calm is fortunate for life in the galaxy's suburbs, where Earth orbits far from the core. Sagittarius A is a hidden anchor, shaping the motions of nearby stars and offering scientists a laboratory for strong gravity. It reminds us that even our familiar Milky Way contains a dark engine at its center. Some galaxies contain black holes billions of times heavier than the Sun. These giants sit in galactic cores and challenge simple ideas about growth. To become so massive, they must have gained enormous amounts of material or merged with other black holes across cosmic time. Some existed when the universe was still young, which makes their size especially puzzling. How did they grow so quickly? Did they begin as unusually massive seeds? Did gas fall into them at extreme rates? Or did early galaxies create perfect feeding conditions? Astronomers search for answers by studying distant quasars, nearby galaxy centers, and computer simulations of cosmic evolution. These immense black holes are not minor details in their galaxies. Their energy can heat surrounding gas, launch jets, and influence whether new stars form. A black hole can be tiny compared with its galaxy in size, yet enormous in consequence. The scale is almost absurd. A region smaller than the solar system can help regulate the fate of billions of stars. Falling gas around black holes can heat brighter than stars. Before material crosses the horizon, it may gather into a rapidly rotating disk. Friction, turbulence, magnetic fields, and compression heat this gas to extreme temperatures. The disk can shine in visible light, ultraviolet, and X-rays, depending on the system. In stellar mass black holes, material may be pulled from a companion star. In galactic centers, the fuel can come from clouds, disrupted stars, or streams of interstellar gas. The light is not emitted from inside the black hole. It comes from matter outside, during its final struggle with gravity. This is why black holes can be associated with brilliant sources, even though the holes themselves are dark. The surrounding environment becomes the lamp. The closer material moves, the more gravitational energy can be converted into radiation. In the right conditions, this process is more efficient than ordinary nuclear fusion. Darkness, paradoxically, can be surrounded by some of the most intense light in the universe. A black hole can tear a passing star into glowing streams. If a star wanders too close to a massive black hole, gravity pulls more strongly on the near side than the far side. This difference can stretch the star until it is shredded in a tidal disruption event. Some of the torn material is flung outward, while some falls back and forms a bright, hot flow around the black hole. Astronomers see these events as sudden flares from galactic centers that were previously quiet. They can last months or even years, revealing how black holes feed when chance delivers a star too close. The process is violent, but also scientifically valuable. It exposes matter under extreme gravity and lights up regions that might otherwise remain unseen. The name sometimes used for this stretching is spaghettification, and it is more than a dramatic word. It describes a real consequence of gravity changing sharply across distance, turning a star into luminous threads before part of it disappears. Einstein predicted gravity bends light around massive objects. Before general relativity, gravity was usually imagined as a force acting between masses. Einstein described it differently. Mass and energy curve space-time, and light follows the resulting paths. During a solar eclipse in 1919, astronomers measured starlight passing near the Sun and found that the apparent positions of stars had shifted. This result made Einstein famous and changed physics forever. The bending was small, but its meaning was enormous. Light has no rest mass, yet its path responds to gravity because gravity shapes the route itself. Today, this effect is central to astrophysics. It helps reveal hidden mass, test relativity, and study objects too distant or faint to examine otherwise. The idea also has a beautiful simplicity. A beam of light thinks it is traveling straight, but the universe around it has been curved. What looks like a deflection is really geometry speaking. Gravitational lensing can magnify galaxies hidden behind other galaxies. When a massive galaxy or cluster lies between Earth and a more distant object, its gravity can act like a natural telescope. Light from the background source bends around the foreground mass, sometimes creating arcs, rings, or multiple images. This magnification can reveal galaxies that would otherwise be too faint to study. Some of the most distant known galaxies have been found with help from this cosmic lensing effect. The foreground object does not need polished glass or mirrors. Its mass does the work by curving space-time. Lensing can also distort images in ways that let astronomers map the distribution of mass, including invisible dark matter. In rare alignments, the result is almost elegant, a bright ring around the lensing object. More often, it appears as stretched smears of ancient light. Either way, the universe becomes its own instrument, using gravity to bring hidden depths into view. Dark matter reveals itself through gravity, not through light. The phrase sounds mysterious because it is. Dark matter does not announce itself with brightness, color, or chemical fingerprints. It is inferred from motion, structure, and gravitational effects. Stars orbit too quickly in galaxies. Galaxy clusters hold together with more mass than visible matter can explain. Light from distant objects bends as though additional unseen material lies in the way. Each clue points towards something that responds to gravity, but barely interacts with electromagnetic radiation. This makes dark matter difficult to identify. It cannot simply be photographed, and it does not behave like ordinary gas or dust. Yet it appears to be far more abundant than the matter that forms stars, planets, and people. Scientists have proposed several particle candidates, but none has been confirmed. The remarkable thing is that ignorance here is not empty. It is precise. We can measure what dark matter does, even while the question of what it is remains open. Galaxy clusters act like cosmic scales for weighing invisible matter. A galaxy cluster contains hundreds or thousands of galaxies, along with hot gas and dark matter bound together by gravity. To measure its mass, astronomers do not need to gather it piece by piece. They can study the speeds of its galaxies, the temperature of its X-ray emitting gas, and the way it bends background light. All these methods often point to far more mass than the visible galaxies provide. In famous cases, clusters have shown separation between ordinary matter and the main source of gravity after collisions. This gives some of the strongest evidence that dark matter is not just a mistake in counting stars. Clusters are enormous gravitational laboratories, large enough to test how the universe builds structure. They weigh the unseen by showing what it does to everything around it. In their vastness, they help answer a deceptively simple question. how much matter is really there. Dark energy seems to be accelerating the expansion of space. In the late 1990s, astronomers studying distant exploding stars found that the expansion of the universe was not slowing as many expected. It appeared to be speeding up. The name given to the cause is dark energy, though the label is more a placeholder than an explanation. It may be related to the energy of empty space itself. It may point to a deeper modification of gravity on cosmic scales. Whatever it is, it dominates the current large-scale behavior of the universe. Its effect is not obvious in everyday life because gravity, electromagnetism, and local structures overwhelm it nearby. Across immense distances, however, its influence becomes decisive. Galaxies not bound together drift apart at an increasing pace. This discovery changed the expected future of the cosmos. Instead of collapsing or gently coasting, the universe may continue stretching into a colder and more isolated future, driven by something we still do not understand. No one knows what dark energy truly is. The most unsettling part of modern cosmology may not be what scientists have discovered, but what the discovery implies. The majority of the universe's energy budget appears to be in a form whose nature remains unknown. It is not dark matter, because it does not gather into halos around galaxies. It seems smooth, persistent, and connected to the expansion of space. One possibility is the cosmological constant, a term Einstein once introduced into his equations for different reasons. Another possibility is a changing field, sometimes called quintessence. There are also ideas that gravity itself behaves differently over the largest distances. Each explanation has consequences, and each must survive observation. Measurements of supernova, cosmic background radiation, galaxy clustering, and gravitational lensing all help narrow the options. Yet, the central mystery remains. Dark energy is not a small missing detail. It is a sign that our best picture of reality may still be incomplete at the largest scale. The cosmic web links galaxies along vast filaments of matter. On the grandest scales, the universe is not arranged randomly. Galaxies gather along enormous strands, walls, and knots, with great voids between them. This structure grew from tiny density differences in the early universe, amplified over billions of years by gravity. Dark matter formed the underlying scaffolding, while gas fell into the same gravitational pattern and formed stars and galaxies. The result is called the cosmic web. Galaxy clusters sit at dense intersections, like cities at crossroads, while thinner filaments stretch across hundreds of millions of light years. Astronomers map this pattern by measuring galaxy positions and by studying the absorption of light from distant quasars. The web shows that the universe has a texture. It is not merely a scatter of island galaxies in emptiness. It is connected by gravity into a vast architecture, where even the largest structures trace back to minute ripples in the young cosmos. Voids between galaxy clusters are enormous regions of cosmic emptiness. Between the filaments of the cosmic web lie immense regions with relatively few galaxies. These voids can stretch for tens or hundreds of millions of light years. They are not perfectly empty, because stray gas, faint galaxies, dark matter, and radiation still exist there. But compared with rich clusters and crowded filaments, they are cosmic deserts. Their existence helps scientists understand how structure formed. Matter flowed away from under dense regions and gathered where gravity had a stronger grip, making empty places emptier and crowded places more crowded. Voids are also useful for testing cosmology because their shapes and growth depend on gravity, dark matter, and dark energy. There is something haunting about their scale. A spacecraft traveling through one would see very little change for longer than human history can comfortably imagine. These spaces remind us that the universe is not only filled with wonders, it also contains absences so large they become wonders themselves. Galaxies grow by merging and swallowing smaller neighbors. A galaxy may look like a finished object, but its history is often built from collisions and capture. Small galaxies fall into larger ones, stretched by tides until their stars become streams across the halo. Gas clouds are pulled in, stirred, compressed, and sometimes turned into new stars. Over billions of years, this process changes shape, size, chemistry, and motion. Large elliptical galaxies may be the product of repeated mergers, where spiral structures are scrambled into more rounded swarms of stars. Even relatively calm galaxies carry evidence of past meals in faint arcs and shells around them. The process is slow from a human point of view, but relentless in cosmic time. Gravity is patient. It pulls neighbors together and rearranges them into larger systems. A galaxy is therefore not merely born and left alone. It grows through encounter, disruption, and inheritance, carrying traces of smaller worlds it has absorbed. The Milky Way is slowly devouring nearby dwarf galaxies. Our home galaxy is not just a peaceful spiral floating alone. Around it orbit smaller companions, and some are being torn apart by its gravity. The Sagittarius dwarf galaxy is one of the clearest examples. As it loops around the Milky Way, tidal forces strip away stars, leaving long streams that wrap through the galactic halo. These streams are like forensic evidence across the sky. They allow astronomers to reconstruct the path of a galaxy being dismantled. Other faint companions may also be losing material, adding their stars to the Milky Way's outer regions. This means our galaxy is still under construction. Some stars we see today may have formed elsewhere, in smaller systems with their own histories, before being folded into ours. The Milky Way's beauty includes acts of capture. Its halo is partly an archive of vanished dwarf galaxies, stretched into ribbons by gravity. Andromeda is moving toward the Milky Way right now. Most distant galaxies recede as space expands, but nearby galaxies can still be governed by local gravity. Andromeda is part of our local group, and it is approaching across intergalactic space. In several billion years, the two great spirals are expected to begin merging. The event will not be a crash in the ordinary sense. Stars are so widely spaced that direct collisions between them will be extremely unlikely. The galaxies themselves, however, will be transformed. Their disks will distort, streams of stars will arc outward, and gas may be compressed into bursts of star formation. Over time, the two systems may settle into a larger galaxy with a new shape. Earth may no longer exist by then in its present form, because the Sun will have changed dramatically. Still, the prediction is remarkable. The night sky contains a future encounter already on its way, visible as a faint smudge to the naked eye. Stars almost never collide when entire galaxies merge. This is one of the strangest facts about cosmic scale. A galaxy can contain hundreds of billions of stars, yet the distances between them are so enormous that they pass like grains of sand separated by many miles. When two galaxies merge, gravity reshapes orbits and rearranges the whole system. But individual stellar impacts are rare. Gas clouds collide much more readily. They can compress, cool, and ignite waves of star formation. Dust lanes twist into new patterns. Star clusters may form in bright knots where gas piles together. The stars themselves mostly follow new paths through the combined gravitational field. This makes galactic collisions both violent and strangely spacious. The structure of each galaxy can be torn apart, while most of its stars remain physically untouched. A merger is not like two solid objects smashing. It is more like two vast swarms passing through one another, then slowly settling into a new gravitational dance. Spiral arms are regions where star formation often gathers. The arms of a spiral galaxy are not fixed rows of the same stars turning like rigid spokes. They are patterns of density moving through the galactic disk. Gas entering these regions can be compressed, which encourages new stars to form. Young, hot stars then light up the arms with bluish brilliance before they die or drift away. This is why spiral arms stand out so strongly in photographs. They are marked by short-lived stars, glowing gas, and dark dust lanes where future stars may be forming. Older stars are spread more widely through the disk and bulge, contributing to the galaxy's softer background glow. The arms are therefore not merely decoration. They are signs of ongoing activity. They show where the galaxy is still rearranging its gas into new stellar generations. A spiral galaxy is not a static pinwheel. It is a rotating system where patterns guide birth across enormous distances. The Milky Way's dark halo may outweigh its visible stars. Beyond the bright disk, beyond the spiral arms and central bulge, our galaxy is embedded in a much larger halo. Part of that halo contains old stars and globular clusters, but most of its mass appears to be dark matter. We infer this from the motions of stars, gas, satellite galaxies, and stellar streams. The visible Milky Way is only the luminous inner part of a larger gravitational structure. This halo may stretch far beyond the region where most stars shine. Its mass helps hold satellite galaxies in orbit and influences how streams of captured stars move. Mapping it is difficult because it cannot be seen directly. Astronomers use the movement of tracers, like distant stars and dwarf galaxies, to estimate its shape and weight. The result changes how we imagine our home. The Milky Way is not just a glowing spiral. It is a bright island inside a vast invisible envelope. Globular clusters preserve some of the galaxy's oldest stars. These compact swarms can contain hundreds of thousands of stars packed into a roughly spherical shape. Many orbit in the halo of the Milky Way, far from the thin disk where new star formation is common. Their stars are often ancient and poor in heavy elements, which suggests they formed early in the galaxy's history, before many generations of stellar enrichment had occurred. Through telescopes, globular clusters look like glittering balls, dense at the center and fading outward. Inside them, stellar encounters happen more often than in the spacious neighborhoods near the Sun. Some contain unusual objects such as blue stragglers, which appear younger or more massive than expected. These clusters are valuable because their stars share a common origin, making them natural laboratories for studying stellar aging. They are also time capsules. To study them is to examine surviving pieces of the Milky Way's early assembly, still orbiting after billions of years. Some stars formed when the universe held almost no metals. In astronomy, the first generations of stars were made mostly from hydrogen and helium because heavier elements had not yet been built in large amounts. That makes ancient stars especially valuable. Their chemistry is like a fossil record preserved in light. When astronomers split that light into a spectrum, they can see which elements are present in the star's atmosphere. Some stars contain only tiny traces of iron, carbon, or oxygen compared with the Sun. That tells us they formed before many earlier stars had lived and died. These old stars are often found in the Milky Way's halo, moving along unusual paths that may remember the galaxy's early assembly. They are faint, patient witnesses from a time before rocky planets were common. Studying them is like reading the first chapters of cosmic chemistry. Each missing ingredient matters, because absence itself becomes evidence of how young and simple the cosmos once was. Astronomers call every element heavier than helium a metal. This sounds strange at first, because oxygen, carbon, and neon are not metals in everyday language. But astrophysics uses a different shorthand. The earliest cosmos was dominated by hydrogen and helium, with only a small amount of lithium. Nearly everything heavier was made later inside stars, stellar explosions, and compact object collisions. So astronomers group those heavier ingredients together and call them metals. This helps them describe how enriched a star, galaxy, or gas cloud has become over time. A metal-rich star likely formed from material already processed by previous generations. A metal-poor star formed from a more primitive mixture. This single word can therefore carry a whole history of creation, death, and recycling. It tells scientists whether a cloud has been touched by earlier stars and whether it might contain the ingredients needed for rocky worlds. In this language, metallicity is not about shine. It is about memory. The first stars may have been gigantic and short-lived. Before planets, dust, and familiar galaxies, gravity gathered simple gas into the earliest stellar fires. These objects are often called population 3 stars, although none has been directly confirmed. Theory suggests they may have been far more massive than most stars today, because the original gas lacked heavy elements that help clouds cool and fragment into smaller pieces. Without efficient cooling, larger clumps could collapse, creating enormous stars with fierce cores. Their lives would have been brief, perhaps only a few million years, but their impact would have been enormous. They produced the first heavy elements and flooded their surroundings with energetic radiation. Some may have ended in unusually powerful explosions that scattered fresh chemistry into space. Others may have collapsed into black holes, planting seeds for later cosmic growth. These first stars were not simply lights switching on. They were the opening furnaces that began changing the chemical character of everything that followed. No confirmed first-generation star has been found yet. The search is difficult because the earliest stars likely lived quickly and died long ago. If any low-mass examples somehow survived, they would be incredibly rare and faint. Astronomers look for them by searching for stars with almost no heavy elements at all. Such a discovery would be extraordinary, because it would offer a direct sample of matter formed from the original ingredients of the cosmos. So far, scientists have found extremely metal-poor stars, but not one that can be confidently called completely pristine. Another approach is to look far away, where telescopes see deep into the past. The challenge is distance, faintness, and confusion from surrounding light. Webb and future observatories may spot clues in early galaxies or unusual stellar explosions. For now, the first stars remain a missing population. We know they must have existed because later chemistry requires them. Yet their direct light has not been securely caught. Cosmic dust is built from tiny grains made in stellar deaths. It may seem odd that space contains dust at all. Between stars, the material is thin beyond ordinary imagination, yet tiny solid grains drift there. These grains can be made of carbon compounds, silicates, metals, and icy coatings. Many are created when aging stars shed their outer layers or when explosions throw newly formed material outward. Once released, dust becomes astonishingly important. It helps cool gas clouds, shields molecules from harsh radiation, and provides surfaces where chemistry can grow more complex. It also blocks visible light, hiding regions that infrared telescopes can reveal. In photographs, dark lanes across nebulae and galaxies are often dust-absorbing starlight behind them. The same kind of material eventually becomes part of planets, comets, and moons. A speck of interstellar dust is tiny, but it carries a grand history. It is the ash of stars, the seed of worlds, and a quiet participant in cosmic construction. Nebulae can be nurseries where gravity gathers future stars. Some nebulae are beautiful because they are active. Inside cold clouds of gas and dust, gravity can begin to pull material into denser pockets. The process is slow and uneven. Turbulence, magnetic fields, radiation, and shock waves all influence which regions collapse and which disperse. In places like the Orion Nebula, young stars have already ignited inside a glowing environment of leftover gas. Their radiation lights the surrounding cloud and sculpts it into ridges, cavities, and pillars. Nearby, dense knots may still be preparing to form more stars. A nebula is not just a painted background in space. It can be a working environment where raw material becomes stellar architecture. Some of the cloud may turn into stars. Some will be blown away. Some may later gather into disks where planets begin. These regions show that star birth is not clean or simple. It is a turbulent transformation of cold darkness into light. Protostars begin as collapsing pockets inside cold molecular clouds. A star's earliest stage is hidden inside a dense clump of gas and dust. The cloud is cold enough for molecules such as hydrogen and carbon monoxide to survive, and in some places, gravity overcomes internal pressure. As material falls inward, it heats up and forms a central growing object. This is not yet a true star, because sustained hydrogen fusion has not begun. It is a protostar, wrapped in a thick envelope that blocks much visible light. Infrared and radio telescopes are often needed to study these beginnings. Jets can shoot from the poles, while a disk forms around the equator, feeding material inward. The process looks messy, with infall, outflow, rotation, and magnetic fields all working together. Over time, if the object gathers enough mass, its core becomes hot and dense enough to ignite. What began as a cold pocket in a dark cloud becomes a new source of starlight. Planetary systems form from disks around newborn stars. When a young star gathers mass, leftover material often flattens into a rotating disk. This happens because the original cloud had some spin, and rotation becomes more important as the material collapses inward. Inside the disk, dust grains collide and stick. Larger clumps form, then planetesimals, then protoplanets that can clear paths through the surrounding gas and debris. Close to the star, heat favors rock and metal. Farther out, ices can survive, making larger cores and gas giants more likely. Astronomers have imaged disks with rings, gaps, and spirals that may reveal planets forming or disturbing the material around them. Our own solar system likely began this way, which means planets are natural byproducts of star birth rather than rare accidents. A disk around a newborn star is a construction zone. It contains the ingredients for worlds, moons, asteroids, comets, and perhaps, much later, places where chemistry becomes life. Planets can migrate far from where they first formed. A young planetary system is not always stable and tidy. While a planet is still embedded in a disk of gas, gravitational interactions can move it inward or outward. Later, close encounters with other planets can scatter worlds into new orbits. This explains why some giant planets are found extremely close to their stars, even though they likely formed farther out where icy material was abundant. Migration can reshape an entire system. It may deliver icy bodies toward inner rocky planets, disturb asteroid belts, or throw smaller worlds into space. In our own solar system, evidence suggests the giant planets shifted positions early in their history, influencing the arrangement of small bodies that remain today. Planetary orbits are not fixed birth certificates. They are histories written by gravity. A world's current path may be the result of drift, encounter and survival through a crowded youth. Hot Jupiters orbit so close that their years last days. These planets shocked astronomers when they were first found. A giant planet like Jupiter was expected to form far from its star, where cold conditions allow large cores and thick atmospheres to gather. Yet hot Jupiters circle very near their stars, sometimes completing an orbit in only a few Earth days. Their atmospheres are blasted by intense radiation, and some are inflated to larger sizes than expected. Because they are massive and close, they were among the easiest exoplanets to detect using stellar wobbles and transits. They forced scientists to rethink planet formation and migration. Many probably began far from their stars and then moved inward through interactions with a disk or other planets. Their presence can disrupt smaller planets nearby, changing the architecture of the whole system. Hot Jupiters are not common around every star, but they are deeply revealing. They showed that other planetary systems could be far stranger than ours. Some exoplanets rain molten glass in sideways winds. One famous example is a blue gas giant, where the atmosphere contains silicate particles, the same broad family of materials found in glass and rock. The planet orbits so close to its star that temperatures soar, and fierce winds race around the globe. Under such conditions, silicate material can condense into tiny droplets or grains and fall through the atmosphere. But this is not gentle rainfall. The winds may drive the particles sideways at extreme speeds, creating a weather system unlike anything on Earth. The planet's blue color does not come from oceans. It likely comes from scattering by haze in its scorching atmosphere. Exoplanet weather has become a real science because telescopes can study light passing through or reflecting from these worlds. From that light, astronomers infer temperatures, chemicals, clouds, and circulation. The result is astonishing. Weather is not just water and air. On other worlds, it can be glass, metal, and heat. Other worlds may hold oceans deeper than Earth's mantle. Some planets may contain far more water than Earth, not as scattered seas over continents, but as global layers hundreds or thousands of kilometers deep. Pressure in such oceans would become enormous. At great depths, water might transform into exotic high-pressure ice, even while layers above remain liquid. This ice would not be cold in the ordinary sense. It would be created by crushing pressure. Such worlds raise fascinating questions about habitability. On Earth, the ocean interacts with rock through the seafloor, exchanging chemicals that matter for life. If a deep-water planet has high-pressure ice separating the ocean from the rocky interior, that chemical connection could be limited. Yet internal heat, dissolved minerals, and unusual ocean layers might create other possibilities. These planets challenge our simple picture of a habitable world. The blue planet from a distance may not be Earth-like at all. It may be a planet-sized ocean with hidden depths beyond imagination. Circumbinary planets orbit two suns in stable cosmic dances. For a long time, planets around binary stars seemed difficult. Two stars tugging on each other create a changing gravitational environment, and it was unclear how easily planets could survive there. Then astronomers found worlds that circle both stars together. These planets move around the pair as if orbiting a shifting central mass, usually at distances where the orbit remains stable. Their skies would be extraordinary. Days, shadows, seasons, and eclipses could follow patterns unlike anything on Earth. Sometimes one star might pass in front of the other. Sometimes both might shine in the sky at once. The discoveries also showed that planet formation can happen in complicated systems, not only around single stars like the Sun. Many stars in the galaxy belong to pairs or multiples, so this matters deeply for estimating how common planets may be. A circumbinary planet turns a science fiction image into an astrophysical reality. Rogue planets wander through darkness without any parent star. Not every planet remains tied to a sun. Some may be ejected from young planetary systems after gravitational encounters with larger worlds. Others might form directly from collapsing clouds, like small, failed stars. Once free, they drift through interstellar space, receiving no steady daylight from a parent star. From a human perspective, they sound lonely and frozen. Yet some could retain internal heat, thick atmospheres, or subsurface oceans warmed by radioactive decay. Detecting them is difficult because they do not shine by reflected starlight. Astronomers can find some through gravitational microlensing when a rogue planet briefly magnifies light from a background star as it passes in front. These dark travelers expand the meaning of the word planet. A world does not need a sunrise to be real. It can wander between stars, unseen for most of its life, carrying its own geology through the galactic night. Astronomers detect exoplanets when starlight dips slightly. The transit method is beautifully simple in concept and incredibly delicate in practice. If a planet passes between its star and our line of sight, it blocks a tiny fraction of the star's light. The star appears to dim by a small, regular amount. From the depth of the dip, scientists can estimate the planet's size. From the timing, they can calculate its orbit. Repeated transits confirm that the signal is not a random flicker. Space telescopes have used this method to discover thousands of worlds, from giant planets to rocky candidates. The alignment must be just right. So many planets never transit from Earth's viewpoint. Even so, the method has transformed astronomy. A distant world may never be directly seen, yet its shadow can reveal its existence. It is remarkable to think that entire planetary systems can be found because a star blinked slightly and rhythmically across the dark. Stellar wobbles can reveal planets too distant to photograph. A planet does not orbit a star alone. Both bodies orbit their shared center of mass. If the planet is small, the star's motion is subtle, but it can still leave a detectable signature. As the star moves toward and away from us, its spectral lines shift slightly through the Doppler effect. Careful measurements can reveal this rhythmic wobble. The method is especially good at finding massive planets close to their stars, though improved instruments can detect smaller signals over time. It gives scientists a planet's minimum mass and orbital period, and when combined with transits, it can help determine density. That tells us whether a planet is likely rocky, gaseous, or something in between. This technique shows how much information is hidden in starlight. A star that looks steady in the sky may be performing a tiny gravitational dance, pulled by unseen companions too faint and close to photograph directly. Atmospheres around exoplanets can leave fingerprints in passing starlight. During a transit, a small amount of starlight filters through the planet's atmosphere before reaching us. Different molecules absorb specific colors of light, leaving patterns in the spectrum. This allows astronomers to search for water vapor, sodium, methane, carbon dioxide, and other gases on worlds far beyond the solar system. The measurements are difficult because the signal is tiny, often buried in the glare of the star and the noise of instruments. Yet, they are powerful. They can reveal whether a planet has clouds, haze, escaping gas, or unusual chemistry. In some cases, scientists can compare light from the planet's day side and night side to study heat circulation. This turns a distant point of light into a place with weather and air. No spacecraft has to visit. No image of the surface is required. The atmosphere speaks through missing colors, and astrophysics learns to read the absence. Some exoplanets are slowly losing their atmospheres to space. Close to a star, radiation can be intense enough to heat the upper atmosphere of a planet, until gas escapes. This process can create great envelopes or tails of hydrogen and helium streaming away. Small planets are especially vulnerable because their gravity may not hold gas tightly. Over time, atmospheric loss can transform a world. A planet that began with a thick hydrogen envelope might be stripped down to a rocky or icy core. This helps explain why some close-orbiting planets seem to fall into distinct size groups. Their atmospheres may have been sculpted by radiation, impacts, and internal heat. Astronomers study escaping gas by looking for absorption during transits, especially in ultraviolet or infrared wavelengths. The idea is powerful because it shows that planets evolve. Their sizes, climates, and surfaces are not fixed at birth. A world can be peeled by its star across millions or billions of years. Brown dwarfs blur the line between planets and stars. These objects are too massive to be ordinary planets, but not massive enough to sustain long-term hydrogen fusion like true stars. Some can briefly fuse deuterium, a heavier form of hydrogen, but they eventually cool and fade. Brown dwarfs may form like stars from collapsing gas clouds, yet their temperatures and atmospheres can resemble giant planets. Some have clouds made of minerals, strong weather patterns, and faint infrared glows. They occupy a fascinating middle ground that challenges clean categories. Are they failed stars? Are they superplanets? The answer depends partly on how they formed and what they can fuse. Astronomers study them to understand both stellar birth and planetary atmospheres. Because they are dim, many remained hidden until infrared surveys improved. A brown dwarf reminds us that nature does not always respect human labels. Between star and planet lies a whole population of objects, warm, dark, and quietly cooling. Jupiter nearly became a star, but lacked enough mass. The giant planet is mostly hydrogen and helium, like the Sun, which makes the comparison tempting. But composition is not enough. To ignite sustained hydrogen fusion, an object needs far more mass than Jupiter has. The pressure and temperature at its core are impressive, but not close to what a true star requires. Even so, Jupiter radiates more heat than it receives from the Sun, partly because it is still slowly contracting and releasing internal energy. Its strong gravity shaped the early solar system, influenced asteroids and comets, and helped define the architecture of the outer planets. Calling it a failed star would be misleading, because it formed and behaves as a planet. Yet it stands near an interesting boundary in public imagination. It is huge enough to feel almost stellar, but physically far below the threshold. Jupiter shows that size alone does not make a star. Fusion is the key. The Sun formed from a cloud enriched by older stars. Our star was born about 4.5 billion years ago from a collapsing region of gas and dust. That cloud was not pristine. It already contained heavier elements made by earlier generations of stars. We know this because the solar system contains rock, metal, carbon chemistry, and radioactive isotopes that could not have existed in the first simple gas of the cosmos. Some evidence even suggests a nearby stellar explosion may have contributed material or helped trigger collapse, though the details are debated. The Sun is therefore not a first act. It is part of a long chain of cosmic recycling. The material around it formed planets, asteroids, comets, and the bodies of living things. This makes our system a second or later generation creation. Before Earth had oceans or continents, older stars had already lived, made new elements, and returned them to space. The Sun inherited their ashes and turned them into daylight. Solar wind constantly streams charged particles through the solar system. The Sun does not only emit light. Its outer atmosphere releases a flow of charged particles, mostly protons and electrons, moving outward in all directions. This stream fills interplanetary space and interacts with planets, moons, comets, and magnetic fields. Earth is protected by its magnetosphere, which deflects much of the solar wind, but some particles are guided toward polar regions. Around comets, solar wind helped shape ion tails that point away from the sun. Far beyond the planets, the wind eventually slows where it meets the interstellar medium, forming a boundary region around the sun's influence. Spacecraft have traveled through that distant frontier and measured changes in particles and magnetic fields. The solar wind reminds us that the solar system is not empty. It is immersed in a moving environment created by our star. Every planet orbits inside a vast invisible breeze of charged matter. Aurorae happen when solar particles meet planetary magnetic fields. The glowing curtains seen near Earth's poles begin far above the surface. Charged particles from space are guided by magnetic field lines toward the upper atmosphere. There, they collide with atoms and molecules, transferring energy that is released as colored light. Oxygen can produce green and red emissions. Nitrogen can add purples, blues, and pinks. Earth is not alone in this display. Jupiter and Saturn have powerful aurorae, driven by their strong magnetic fields and by interactions with their moons and solar wind. Even Mars, with only patchy crustal magnetism, has unusual auroral events. These lights are beautiful, but they are also diagnostics. By studying them, scientists learn about magnetic fields, atmospheric chemistry, and space weather. An aurora is a visible conversation between a planet and its star. It turns invisible particles and magnetic geometry into a shimmering map written across the upper air. Cosmic rays strike Earth from violent events across the galaxy. Despite the name, these are not rays in the ordinary sense. They are high-energy particles, often protons or atomic nuclei, moving at nearly light speed. Many come from beyond the solar system, accelerated by powerful environments such as supernova remnants, stellar winds, or other energetic regions. When they hit Earth's atmosphere, they smash into air molecules and create showers of secondary particles. Some of those particles reach the ground or pass through our bodies without notice. Cosmic rays can affect spacecraft electronics, pose risks to astronauts, and even help scientists study hidden structures on Earth through particle imaging. Their exact origins at the highest energies remain an active mystery. Magnetic fields twist their paths, making it hard to trace them backward. Each particle is like a tiny messenger, but has crossed space at tremendous speed. By the time it arrives, it carries hints of violent places we cannot easily visit. Gamma-ray bursts are among the brightest explosions ever measured. For a few seconds, one of these events can release more energy than the sun will emit over its entire lifetime. They were first detected by satellites watching for nuclear tests, which makes their discovery story especially unusual. Later, astronomers learned that many come from deep space, not from Earth's neighborhood. Some are linked to the collapse of massive stars into black holes. Others are associated with mergers of compact stellar remnants. Their gamma rays arrive as sudden flashes from random directions, followed by fading afterglows in X-rays, visible light, infrared, and radio. Because they are so bright, they can be seen across enormous distances, acting as probes of the early universe. Yet they are also narrow and brief, which makes them difficult to catch. A gamma-ray burst is astrophysics at its most intense. For a moment, a distant point becomes one of the most luminous events nature can produce. A nearby gamma-ray burst could damage a planet's atmosphere. The danger depends on distance, direction, and intensity. Many gamma-ray bursts release much of their energy in narrow jets, so a planet would need to lie in the path. If such an event occurred close enough and pointed toward Earth, high-energy radiation could alter the chemistry of the upper atmosphere. It might reduce protective ozone and allow more ultraviolet light to reach the surface. Some scientists have explored whether ancient extinction events could be linked to this kind of cosmic radiation, although evidence remains uncertain. The important point is not that danger is imminent. Nearby, correctly aimed bursts are rare. The idea matters because it shows that life on a planet is connected to its galactic environment. Habitability is not only about oceans, air, and distance from a star. It also depends on what violent events happen nearby across deep time. A planet lives under a sky with history. Fast radio bursts release enormous energy in milliseconds. These flashes are brief, powerful pulses of radio waves from far beyond our galaxy. Some last only a few thousandths of a second, yet in that instant, they can emit as much energy as the sun releases over days. Their signals are dispersed as they travel, with lower radio frequencies arriving slightly later than higher ones. That delay reveals how much material the burst passed through, making fast radio bursts useful probes of otherwise hard-to-see gas between galaxies. At first, they seemed completely mysterious because they appeared once and vanished. Then, repeating sources were found, which opened new ways to study their environments. Some come from regions with strong magnetic fields or active star formation. Their exact origins may not all be the same. The brevity is what makes them so compelling. A remote object can speak for a millisecond, and that tiny pulse can carry information across billions of light years. Some fast radio bursts come from distant magnetars. The magnetar connection became stronger when a magnetar in our own galaxy produced a bright radio burst alongside high-energy radiation. This showed that at least some fast radio bursts can be generated by highly magnetized neutron stars undergoing sudden activity. In distant galaxies, repeating bursts may come from similar objects, especially young magnetars in energetic environments. The mechanism is still being studied. Magnetic fields may snap, rearrange, or drive shocks that create coherent radio emission. Not every burst has to share the same source, and that is part of the excitement. Astrophysics often begins with a mystery class, then discovers that nature uses more than one pathway. Magnetars provide a plausible engine because they store extreme magnetic energy in a compact object. When that energy shifts suddenly, the result can be a flash detectable across intergalactic distances. A star smaller than a city may announce itself across the cosmos in a blink. The universe became transparent when atoms first captured electrons. In its earliest hot phase, matter existed as a plasma of free electrons and atomic nuclei. Light could not travel far because it kept scattering off loose electrons. As expansion cooled everything, electrons began to combine with nuclei, forming neutral atoms. With fewer free electrons in the way, photons could finally move through space without constant interruption. This transition is called recombination, although it was really the first widespread combination of electrons with nuclei. The light released from that era still surrounds us today as the cosmic microwave background, stretched by cosmic expansion into longer wavelengths. This moment matters because it marks the beginning of a universe we can directly observe with light. Before it, the cosmos was opaque to electromagnetic signals. After it, radiation could cross vast distances. Transparency turned the universe into something readable. It allowed the oldest light to begin its journey, carrying patterns from the young cosmos into modern detectors. Before the first stars, the cosmos passed through darkness. After the early glow faded into microwaves, there was a long period with no stars to shine. Gas filled space, gravity slowly amplified slight density differences, and matter gathered into the first structures. This era is often called the Cosmic Dark Ages. It was not empty, and it was not inactive. It was a time of preparation. Hydrogen and helium drifted in expanding space, while dark matter helped build gravitational wells. Inside those wells, gas could collect, cool, and eventually collapse enough to ignite the first stars. No human telescope can see ordinary starlight from before stars existed, so scientists study this era indirectly through models, background radiation, and future searches for signals from neutral hydrogen. The darkness was not a failure of creation. It was the pause before the first lights. In that interval, the universe was assembling the conditions that would make galaxies, chemistry, and later worlds possible. Reionization ended the cosmic dark ages with newborn starlight. After the first stars ignited, their radiation began changing the universe around them. The space between galaxies was filled mostly with neutral hydrogen, which absorbs certain kinds of ultraviolet light. Young stars and early galaxies poured out energetic radiation that stripped electrons away from hydrogen atoms, turning much of the intergalactic gas back into plasma. This process did not happen everywhere at once. It spread in bubbles around the earliest sources of light, then those bubbles grew and merged. In this way, the universe slowly became easier for light to cross. Reionization is one of the great transitions in cosmic history. It marks the time when the first luminous structures began reshaping the environment beyond themselves. Scientists study it through distant galaxies, quasar light, and the faint signatures of ancient hydrogen. It is the moment when the universe moved from darkness into a new era of visibility, structure, and discovery. The Big Bang was expansion everywhere, not an explosion somewhere. The popular picture of a blast flying outward into empty space is misleading. The early universe was not a fireball expanding from one location into a surrounding void. Space itself was growing, and every region was part of that expansion. There was no outside room waiting for it. Every distant galaxy today is not racing away from a central point we can find. Instead, distances between unbound galaxies increase because the scale of space changes. Imagine every place seeing other faraway places recede, with no privileged center. That is closer to the modern picture. The name Big Bang survived because it is vivid, but the event it describes is subtler and stranger. It is the beginning of the universe's hot, dense, expanding state, not an ordinary explosion inside the universe. This matters because it changes the question. We are not asking where it happened. We are asking how all of space evolved. Inflation may have stretched tiny quantum ripples across the universe. One leading idea about the universe's earliest fraction of a moment is called cosmic inflation. It proposes that space expanded incredibly rapidly, smoothing the cosmos and stretching microscopic fluctuations to enormous scales. These fluctuations began as quantum uncertainty, the tiny, restless behavior built into fields themselves. Inflation would have pulled those small variations far apart, turning them into the seeds of later structure. Afterward, some regions were slightly denser than others. Gravity slowly amplified those differences until galaxies, clusters, and the cosmic web could form. Inflation helps explain why the universe looks so uniform in every direction. It still contains the small irregularities needed to build everything interesting. It also makes predictions that can be tested in patterns of ancient radiation. The idea is still being examined and refined. If it is right, then the largest structures in the sky began as almost unimaginably tiny ripples, stretched by a burst of expansion beyond everyday thought. Those ancient ripples later grew into galaxies and clusters. The universe did not begin with finished structures. It began with slight differences in density, so small that they would seem almost meaningless. Yet gravity is patient. Regions with a little more matter pulled in more material. Regions with a little less gave matter up more easily. Over hundreds of millions and then billions of years, that quiet imbalance became dramatic. Gas gathered into the first stars and galaxies. Dark matter helped build larger gravitational frameworks. Galaxies collected into groups, and groups gathered into clusters. The grand architecture of the modern universe was not imposed all at once. It grew from tiny contrasts, amplified by time. This is one of the most powerful ideas in astrophysics. The great shining systems we admire are connected to minute patterns in the young cosmos. A galaxy cluster containing thousands of galaxies can trace its ancestry to a small unevenness in the early universe's glow. The observable universe is only the path light has reached us from. There is a limit to what we can see, not necessarily because the universe ends there, but because light has had only a finite time to travel. The universe is about 13.8 billion years old, yet the observable region is much larger in radius than 13.8 billion light-years because space expanded while the light was traveling. Our cosmic horizon surrounds us in every direction. Beyond it may be more galaxies, more matter, and more space, but their light has not had time to arrive. This boundary is not a wall a spacecraft could crash into. It is a horizon of information. Every observer elsewhere would have their own observable universe centered on them. That thought is humbling. The universe we can measure is vast beyond ordinary imagination, but it may be only a portion of the whole. Astrophysics teaches us that even our deepest view has a border made by time. More universe may exist beyond our cosmic horizon. The part we observe could be only a local patch of something far larger. Current measurements suggest space is very close to flat on large scales, which is consistent with a universe that extends far beyond what light has revealed to us. It may even be infinite, although that remains unknown. If regions beyond our horizon exist, they're not hidden behind a physical curtain. Their signals simply cannot reach us yet, and some may never reach us because expansion carries them too far away. This idea is difficult because science depends on observation. We can make careful inferences from geometry, background radiation, and cosmological models, but we cannot directly inspect those unreachable regions. Still, the possibility changes how we imagine reality. The observable universe, with all its galaxies and wonders, may be only one visible chamber in a structure too large to survey. Our cosmic map may have edges only because our information does. The universe has no known center or outer edge. Everywhere we look on the largest scales, the cosmos appears broadly similar. Galaxies spread in all directions, and the expansion looks much the same from every viewpoint once local motions are accounted for. This does not suggest that Earth is central. It suggests that the universe has no special center within space. The expansion happens throughout space rather than away from one middle point. The question of an outer edge is equally subtle. If space is infinite, there is no boundary. If it is finite but curved in a certain way, it might still have no edge, much as Earth's surface has no edge even though it has a finite area. The difference is that the universe involves three-dimensional space rather than a two-dimensional surface. This is hard to visualize, but the lesson is clear. The cosmos is not like a room with walls. It may be a geometry without borders. Cosmic expansion makes very distant galaxies recede faster than light. This sounds as if it breaks the universe's speed limit, but it does not. The rule that nothing travels through space faster than light applies locally. Cosmic expansion is different because it changes the distance between places as space itself stretches. Very distant galaxies can recede from us at effective speeds greater than light because more and more space is being created between us and them. Those galaxies are not flying through nearby space faster than a light beam would. They are carried by the growth of the cosmic scale. This distinction is essential to modern cosmology. It explains why some regions can become permanently unreachable, even if we sent a signal at light speed today. The light would move as fast as nature allows, but the expanding distance might still win. The universe is therefore not only immense, it contains horizons shaped by expansion, where distance becomes a kind of one-way silence. That motion does not break physics because space itself expands. Relativity places limits on how objects move through their local surroundings. It does not forbid the large-scale metric of the universe from changing. In everyday life, space feels like a fixed stage. In cosmology, the stage itself evolves. Galaxies bound by gravity, such as those in the same group, can resist expansion. But on vast scales, where galaxies are not bound to each other, the expansion of space increases their separation. This is why there is no contradiction in saying that very distant galaxies recede faster than light. No spacecraft is locally outrunning a nearby beam. No message is being sent faster than causality allows. The geometry between regions is changing. It is a subtle idea, but it is one of the most important shifts in thinking that astrophysics offers. Space is not simply where events happen. It has behavior of its own, and that behavior shapes what can never be connected. The future sky may one day lose most distant galaxies. As expansion continues, galaxies beyond our local gravitational neighborhood will become harder to see. Their light will be stretched to longer and longer wavelengths, fading into signals too weak and cold for future observers to detect. Eventually, a civilization in the far future might see mainly the merged remains of nearby galaxies, with little direct evidence of the wider universe beyond. The cosmic microwave background would also become stretched and diluted beyond practical discovery. This is a remarkable thought. We live at a time when the universe is old enough to contain rich structure, but young enough for distant signals still to reach us. Our era may be especially fortunate for cosmology. The sky contains clues that will not remain equally accessible forever. The future universe may not be empty, but it may look isolated. Knowledge that seems natural now depends on living during a window when the cosmos is still readable. Astrophysicists use spectra to read what distant objects are made of. When light is spread into its component colors, it becomes more than brightness. It becomes information. Atoms and molecules absorb or emit light at specific wavelengths, leaving patterns like barcodes in a spectrum. Hydrogen, helium, oxygen, sodium, and countless other ingredients each have recognizable signatures. By studying these lines, astronomers can identify the chemistry of stars, nebulae, galaxies, and planetary atmospheres without touching them. Spectra can also reveal temperature, pressure, density, motion, and magnetic fields. This method is one of the great miracles of astrophysics. A star may be impossibly distant, yet its light carries a record of the matter within its outer layers. A cloud may be invisible to the eye, yet its spectrum can announce the molecules inside. Spectroscopy turns telescopes into remote laboratories. The universe sends light across space, and hidden inside that light is a list of ingredients written by atoms themselves. A star's color reveals its surface temperature. Color in stars is not just decoration. It is a physical clue. Hotter stars emit more of their light at shorter wavelengths, giving them a blue or bluish-white appearance. Cooler stars emit more strongly at longer wavelengths, making them look orange or red. The Sun sits between these extremes, with a surface temperature that gives it a white light that appears yellowish from Earth's atmosphere. This relationship comes from thermal radiation, the way hot objects glow according to temperature. By measuring a star's color carefully, astronomers can estimate how hot its visible surface is. Combined with brightness and distance, that temperature helps reveal the star's size, stage of life, and likely future. The idea is wonderfully direct. The color of a tiny point in the night sky contains a thermometer reading from far away. Even before detailed spectra are considered, the shade of starlight begins telling the story. Doppler shifts show whether objects move toward or away from us. Light changes when its source moves relative to the observer. If an object approaches, its wavelengths are compressed slightly toward the blue. If it recedes, they are stretched toward the red. Astronomers measure this effect in spectral lines, comparing observed wavelengths with known laboratory values. The shift reveals motion along our line of sight. It has been used to measure stellar orbits, discover exoplanets, track gas flows, and show that distant galaxies are generally receding. The same principle appears in sound when a siren changes pitch as it passes, but with light, it becomes a tool for mapping the universe. Sometimes the shifts are tiny, requiring extraordinary precision. Sometimes they are enormous, revealing cosmic expansion across billions of light years. The Doppler effect turns motion into a readable signal. An object does not need to visibly move across the sky. Its light can whisper whether it is coming closer or drifting away. Radio astronomy can see cold gas that visible telescopes miss. Visible light reveals stars beautifully, but not every important part of the universe shines that way. Cold hydrogen gas emits radio waves at a famous wavelength of 21 centimeters. By detecting that signal, astronomers can map vast clouds of neutral hydrogen in and around galaxies. This gas is often the raw material for future star formation. Radio telescopes can also study molecules, pulsars, cosmic magnetic fields, and energetic jets. They work during the day and can penetrate dust that blocks visible light. Their dishes may look less dramatic than optical observatories, but they open a different universe. Some structures that appear dark in ordinary images become rich and detailed in radio maps. The Milky Way's spiral structure, for example, has been studied partly through radio observations because we sit inside the dusty disk. Radio astronomy proves that the cosmos cannot be understood through one kind of light alone. Cold things still have voices. Infrared telescopes peer through dust that hides newborn stars. Dust clouds can block visible light, turning active star-forming regions into dark patches. Infrared radiation, with longer wavelengths, can pass through dust more easily. It also reveals cooler objects that do not glow strongly in visible light. This makes infrared astronomy essential for studying protostars, planet-forming disks, brown dwarfs, and distant galaxies whose light has been stretched by cosmic expansion. A region that looks opaque to the eye may blaze with activity in infrared images. Young stars hidden inside cocoons of gas and dust become detectable. Warm dust around newborn systems glows, showing where planets may be assembling. Infrared telescopes must often be kept very cold because heat from the telescope itself can interfere with the faint signals being measured. The reward is a deeper view into places where the visible universe is veiled. Infrared light lets astrophysicists watch beginnings that would otherwise remain concealed. X-ray telescopes reveal extremely hot gas around violent objects. Earth's atmosphere blocks most cosmic X-rays, which is fortunate for life but inconvenient for astronomy. To observe them, telescopes must work in space. X-rays come from some of the hottest and most energetic environments in the universe. They reveal gas heated to millions of degrees, material falling toward compact objects, shock waves from explosions, and the hot atmospheres of galaxy clusters. Because X-rays are so energetic, focusing them requires special mirror designs that let them glance at shallow angles rather than strike head-on. The images and spectra they produce uncover processes invisible in ordinary light. A galaxy cluster may look like a collection of galaxies in visible images, but in X-rays it can glow with vast clouds of hot gas that contain more ordinary matter than the galaxies themselves. X-ray astronomy shows the universe in its high-energy mood, where gravity, heat, and speed become extreme. Neutrinos can escape stellar cores and supernova explosions. Neutrinos are ghostly particles that interact only weakly with matter. Trillions pass through your body every second without effect. This strange reluctance to interact makes them hard to detect, but it also makes them precious messengers. Light from a star usually comes from its outer layers, but neutrinos can emerge from deep nuclear regions and from the core collapse of massive stars. In a supernova, they carry away an enormous amount of energy and can arrive before visible light escapes the surrounding material. Detectors on Earth are buried deep underground or underwater to shield them from other particles, waiting for rare interactions. When neutrinos are caught, they offer information from places light cannot easily leave. They are like whispers from the heart of violent events. Their very elusiveness makes them valuable. Because they barely touch matter, they can cross regions that would stop other signals and bring news from hidden cores. Supernova, 1987, has sent neutrinos through Earth before its light. In February of 1987, astronomers observed the brightest nearby supernova in centuries. It occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Before the visible brightening was fully recognized, underground detectors had already recorded a small burst of neutrinos. Only a few were caught, but those few were historic. They confirmed that core collapse supernova release immense energy in neutrinos, just as theory predicted. The event also gave scientists a rare nearby laboratory for watching the aftermath of a stellar explosion evolve. Rings of gas around the star lit up over time as the expanding blast wave reached them. This supernova connected prediction, particle detection, and telescope observation in a single cosmic story. It showed that astrophysics is not limited to light. A dying star can send several kinds of messages, and the first to arrive may be almost invisible particles slipping through Earth as if it were mist. The Higgs field helps explain why particles have mass. Mass is not simply an obvious property that particles carry without explanation. In modern particle physics, many fundamental particles gain mass through interaction with the Higgs field, which exists throughout space. The Higgs boson is the particle associated with that field, discovered at the Large Hadron Collider after decades of prediction. This may sound far from astrophysics, but the connection is deep. The behavior of matter in the early universe depended on the properties of fundamental fields. The masses of particles influence how atoms form, how stars burn, and how structure becomes possible. Without the right particle masses, the universe could look radically different. The Higgs field is therefore part of the hidden foundation beneath every galaxy and star. It is not a substance you can scoop up. It is a field woven into the rules of reality. Its existence helps explain why matter can assemble into the cosmic structures we observe. Antimatter exists in space, but matter dominates the universe. For many particles, there is an antimatter counterpart with the same mass and opposite charge or related quantum properties. When matter and antimatter meet, they can annihilate into energy. Particle accelerators create antimatter routinely in tiny amounts, and cosmic ray interactions can produce it naturally. Astronomers also detect positrons, the antimatter partners of electrons, in certain high-energy environments. Yet the universe around us is overwhelmingly made of matter. Stars, planets, gas clouds, and people. are not half matter and half antimatter. If large regions of antimatter galaxies existed nearby, their borders with matter regions should produce strong annihilation signals, which we do not see. This imbalance is one of the great clues from the early universe. Matter and antimatter seem closely paired in the laws of physics, but the cosmos chose one side almost completely. The result is everything familiar. The mystery is why there was anything left to build with at all. Scientists still do not know why matter survived antimatter. The early universe likely produced matter and antimatter in nearly equal amounts. If the balance had been perfect, particles and antiparticles would have annihilated, leaving mostly radiation and almost no material for stars or planets. Yet a tiny excess of matter remained. That excess became the galaxies, worlds, and bodies we know. Explaining it requires conditions that allow matter and antimatter to behave slightly differently in key ways. Physicists have found some forms of asymmetry in particle behavior, but not enough to account for the observed cosmic abundance. This puzzle is called baryogenesis, and it links the smallest particles to the largest structures. It may involve physics beyond current models, hidden processes in the early universe, or particles not yet discovered. The question is simple to ask and staggering in consequence. Why is there something rather than a universe of light alone? Every atom is evidence that matter won a tiny, decisive victory. The sun's core makes light that escapes slowly through countless collisions. Energy produced in the core does not fly straight to the surface. It begins as high-energy radiation in a dense environment where particles are packed closely together. Photons are repeatedly absorbed and re-emitted, scattering through the solar interior in a random walk. A photon's direction changes again and again, so its outward journey can take an enormous amount of time. By the time energy reaches the visible surface, it has been redistributed into the sunlight we know. From there, it crosses space to Earth in minutes. This means the warmth on your face has a complicated past. Its energy was made deep inside the sun, delayed by countless interactions, then finally released from the photosphere. The sun appears steady because this vast interior process smooths and regulates the flow. What feels like instant daylight is the final step of a long escape from a nuclear furnace hidden beneath layers of plasma. Sunlight reaches Earth after 8 minutes of travel. The distance between Earth and the sun is so great that even light needs time to cross it. When sunlight leaves the solar surface, it races through space at the fastest speed allowed by nature. It still takes a little over 8 minutes to arrive here. That means we never see the sun exactly as it is in the present moment. We see it as it was minutes earlier. This delay is small compared with the years or billions of years involved in distant astronomy, but it is enough to remind us that looking into space always involves looking into the past. The same sunlight then powers weather, photosynthesis, ocean currents, and vision itself. It is a messenger carrying energy from a star to a planet at just the right distance for liquid water to persist on the surface. Every sunrise is already slightly historical, a fresh arrival from a star we see by delayed fire. Heliosismology lets astronomers study vibrations inside the sun. The sun rings with subtle oscillations. Its surface rises and falls in patterns caused by sound waves traveling through the solar interior. By measuring these motions, scientists can infer conditions beneath the visible surface. The method is similar in spirit to using earthquakes to study Earth's interior, although the sun is made of hot plasma rather than rock. Different waves travel through different depths, carrying information about temperature, density, rotation, and flows. Heliosismology has revealed that the sun does not rotate as a solid object. Its equator turns at a different rate from higher latitudes, and its interior has distinct layers of motion. This field allows astronomers to probe a star we cannot enter. The surface becomes an instrument panel, trembling with signals from below. Instead of cutting the sun open, scientists listen to its vibrations. Those patterns turn a glowing disk into a transparent object, at least to careful mathematics. Asteroseismology uses starquakes to reveal hidden stellar interiors. Other stars also pulse, tremble, and resonate. Space telescopes can measure tiny changes in brightness as waves move through stellar interiors. Those brightness variations may look slight, but they carry rich information. By studying the frequencies of these oscillations, astronomers can estimate a star's size, mass, age, internal rotation, and evolutionary stage. This is especially useful because stars are usually seen only as points of light. Asteroseismology gives them inner structure. It can distinguish between stars that look similar on the outside but are at different stages inside. It has also improved the study of exoplanets, because knowing a host star more accurately helps determine the size and age of its planets. The idea is wonderfully elegant. Stars have music too faint for ears, written in light rather than sound. When scientists decode that rhythm, they learn what is happening beneath surfaces that no spacecraft could ever touch. Some stars pulse because their outer layers trap and release heat. In certain stars, opacity changes inside partial ionization zones can create a natural engine for pulsation. When a layer traps heat, pressure builds and the star expands. As expansion changes the layer's conditions, heat escapes more easily, and the star contracts again. This cycle can repeat with striking regularity. The result is a variable star whose brightness rises and falls like a slow breath. Cepheids and other pulsating stars are important not only because they are physically fascinating, but because their rhythms reveal properties that can be measured across great distances. Their light curves become signatures of internal physics. Instead of seeing a star as a fixed lamp, we see it as a dynamic body with layers that store, release, and respond. Pulsation turns hidden structure into visible timing. A star's brightness can become a clock, a diagnostic tool, and a clue to distances far beyond the reach of ordinary measurement. Cepheid stars help to measure the scale of the universe. Cepheids are pulsating stars with a crucial relationship between their period and their true brightness. The longer the pulsation period, the more luminous the star tends to be. Once this relationship was understood, astronomers could compare a Cepheid's true brightness with how bright it appears from Earth. The difference reveals distance. This made Cepheids cosmic measuring rods. They helped show that some fuzzy patches in the sky were not nearby nebulae inside the Milky Way, but separate galaxies far beyond it. That discovery expanded humanity's sense of the universe dramatically. Cepheids also helped calibrate later methods for measuring still greater distances, including certain supernovae. Their importance comes from regularity. A star that brightens and dims in a predictable rhythm can tell us how far away it is. The scale of the cosmos was not found by traveling through it. It was found by watching stars breathe. Henrietta Leavitt discovered the pattern that made cosmic distances possible. Working with photographic plates at Harvard College Observatory, Leavitt studied variable stars in the Magellanic Clouds. Because stars in each cloud were roughly the same distance from Earth, differences in their apparent brightness could be compared meaningfully. She noticed that certain variables with longer periods were brighter. This period luminosity relationship became one of the most important tools in astronomy. It allowed other astronomers to measure distances far beyond the reach of parallax. Her work laid the foundation for proving that the universe extended far outside the Milky Way. Leavitt did not have the fame during her lifetime that her discovery deserved. Yet modern cosmology rests partly on her careful measurements. The story is powerful because it shows how patient attention to repeated patterns can change humanity's place in the cosmos. A woman examining glass plates found a rhythm in starlight, and that rhythm opened the scale of the universe. Vera Rubin's galaxy measurements helped reveal the dark matter mystery. Rubin studied how stars and gas move in spiral galaxies. The expectation was that material far from the center would orbit more slowly if most mass were concentrated in the visible parts. Instead, rotation curves often stayed surprisingly flat. Outer regions moved too fast to be explained by the light we could see. Rubin's observations, along with related work by others, strengthened the case that galaxies contain large amounts of unseen mass. Her measurements were careful, persuasive, and difficult to ignore. They did not identify the hidden matter, but they showed that something important was missing from the visible picture. This helped make dark matter a central problem in astrophysics rather than a minor curiosity. Rubin's legacy is more than a discovery about galaxies. It is a reminder that the universe can reveal its secrets through motion. Stars on the outskirts of galaxies were telling a story, and she listened closely enough to hear it. Astrophysics keeps turning the night sky into a testable story. For most of human history, the stars inspired myth, navigation, calendars, and wonder. Modern science did not remove that wonder. It gave it sharper tools. A point of light can be measured for brightness, color, chemical fingerprints, motion, age, and distance. A patch of darkness can reveal hidden dust, cold gas, or the pull of unseen matter. A faint signal in a detector can announce a collision that happened before complex life existed on Earth. What makes astrophysics so compelling is that its claims are not simply grand. They're checked against the sky. The universe becomes a story with evidence in every chapter. Some pages are written in light. Some are written in particles, waves, or gravity. Many remain unread. Yet the method is steady. Ask a bold question, build an instrument, compare the answer with reality, and let the cosmos correct you. The night sky becomes not a ceiling, but an invitation. And so, we come gently back from the farthest edges of the cosmos. Tonight, we have drifted through the strange and beautiful workings of astrophysics. We have watched time bend near black holes and seen how ancient stars shaped the atoms inside our bodies. We have followed galaxies as they gather, collide, and grow. We have listened for ripples in space-time, traced invisible matter through its gravity, and looked back toward the first light that ever moved freely through the universe. We have wandered among neutron stars, glowing nebulae, distant exoplanets, and the hidden forces that stretch space itself. And through it all, one idea keeps returning. The universe is not still. It is moving, changing, forming, fading, and beginning again in ways too vast to hold all at once. But you don't need to hold it all now. Let the stars soften into points of light. Let the galaxies drift farther away. Let the great questions rest for a while, like instruments falling silent after a long and beautiful song. If you enjoyed this journey, you're always welcome to like, subscribe, or leave a thought below. It helps other curious souls find their way here too. And if you happen to still be awake, there should be another calm exploration waiting on the screen, ready whenever you are. But for now, there is nothing more to learn, nothing more to follow, and nothing more to do. Let your shoulders loosen. Let your breathing find its own slow rhythm. Imagine the night sky above you, wide and steady, with every distant star shining in its place. The universe will keep turning. The light will keep traveling. And you can simply rest. Sleep well, and good night.